Thank you, Simon, very much for the kind presentation. So, as Simon mentioned, I'm working at the University of Pavia, that is located next to Milan in the northern part of Italy. I will start with the outlook of this presentation. So first, I will start with the introduction, presenting the reasons behind my study, and obviously presenting the passivation. Later, in the second part, I'm going to present two types of passivation, the so-called cation or molecular passivation, and the second one called low-dimensional perovskite passivation. I'm going to show you how we can control between one or the other and the effects they have in perovskite solar cells. Finally, in the last part of my talk, I'm going to present the experimental result I achieved in the labs here in Pavia, presenting the characterization, the efficiency we achieve, and also the stability. So for the first slide, I will start with this well-known chart that is a real chart of the most efficient devices. I work on a perovskite solar cell single junction, and as it's possible to observe, we passed from 14% of efficiency up to 27%. But despite this is a well-known chart, the important part that I would like to mention in this slide is that starting from 2018-19, we achieved an efficiency above 20% thanks to surface passivation. And we managed to get these world records just thanks to this step. And a perovskite solar cell is made with the active layer, that is the perovskite, and two extraction layers. We can find, depending on the first extraction layer, we find according to the light path, the PIN structure or NIP structure, respectively inverted and regular structure. The passivation usually is on top of the surface of perovskite, and the reason for this is that basically here is where most of the defects are located, and also where the grain boundaries is possible in an easy way to passivate. And basically, for perovskite solar cell, we can use whatever we want to passivate. There are papers where they use capsaicin, coffee, and whatever, and we get an enhancement in VOC, and basically we are happy. We have a more efficient solar cell, and so for that reason, most people focus on this. But the best candidate for the passivation, the most reported, are these organic salts that basically are also precursor of a low-dimensional perovskite that I'm going to present later on. Since they are easy processable, since they are soluble in gentle solvents, they are also easy processable since we can make with gentle solvents, we can use and deposit them just by spin coating. They have a low cost, and so for also this is a good point. And basically they get an enhancement in efficiency and the world records in perovskite solar cells in the recent publications. And how we can perform a passivation? Basically, we drop the solution, usually, as I mentioned before, in IPA, on top of the surface of the 3D perovskite. And basically, we get a nice enhancement in the VOC and maybe in also the other PV parameters. But something that people not always report is that actually with these organic salts, we can get two different passivation. The so-called cation or molecular passivation, where basically is the salt itself that passivate the surface of the 3D perovskite. And so basically the beneficial effects are made without any formation of other materials. And the second passivation that is so-called low-dimensional perovskite passivation, where this organic salt reacts with the top of the surface of the 3D perovskite, forming a pure 2D perovskite in the first case, in the case n is equal to 1, or a quasi-2D perovskite, where between the two organic layers are present more than one lead octaedra, and we can find n equal to 2, 3, 4, and etc. And this is another kind of passivation where the precursor reacts with the 3D perovskite and form this material. But the question that may pop in your mind is how we can control the passivation. Well, actually, together with the Sargent group, we focus on studying the recent scientific publication to find the factors that can determine one passivation or the other. And we find 6 factors. The first one is the concentration. In fact, low concentration, most likely you get a cation passivation. Meanwhile, with a higher one, you get the second one. The second factor is the temperature. In fact, performing a deposition at room temperature without an additional annealing step, you get the cation passivation. Meanwhile, performing this additional step, basically you are giving the activation energy and helping the formation of a low-dimensional perovskite. The third factor is the solvent polarity, and this is basically related to the fact that if you dissolve also the first layer of the 3 perovskite, you basically are giving to the deposition the possibility to form a low-dimensional perovskite because you are giving the material for the formation of this kind of material. Otherwise, if you use an orthogonal solvent like chlorobenzene, basically you are helping the cation passivation. Also, the perovskite composition plays a key role in the kind of passivation, since the inorganic bonds are stronger. So for that reason, it's difficult to perform and have a formation of a low-dimensional perovskite that is much easier with an methylammonium or formamidinium based perovskite. And also the steric hindrance of the precursor itself play a key role, since if we have small molecules or atoms like bromide, chloride, or iodide, we have most likely a low-dimensional perovskite passivation. Meanwhile, when we have a more steric hindrance anions and also cations, we have most likely a molecular or cation passivation. Also, I have to mention that I always talk about organic salts, but actually is not the only source we can use, the only precursors we can use. In fact, we can use also amines. And if we are using a formamidinium-based perovskite, basically the reaction is a bit more complex. For this reason, we have most likely a cation passivation. Meanwhile, if we use a MAPI-based perovskite, the reaction is much easy. And for this reason, is most likely we get a formation of a 2D perovskite. So basically, these are the factors that we find. And another topic is about how they affect the perovskite solar cell. So basically, we take the difference between a reference cell and a passivated solar cell and subdivided them in a regular and inverted structure. And as it possible to observe, basically we have an enhancement in the voltage, in the VOC, in almost all the cases. Meanwhile, if we look at the current and the fill factor, we have an enhancement, a positive value in the regular structure, almost in all the cases. Meanwhile, looking at the inverted structure, when we are forming a low-dimensional perovskite, we have a detrimental effect. Looking at the efficiency, we can observe that basically in the regular structure, there is a positive value. Meanwhile, in the inverted structure, we have a negative value when we are forming a low-dimensional perovskite. Meanwhile, molecular passivation have always a positive value in both architecture. But we do not have to be afraid about a negative value, because still, if we have a detrimental effect in efficiency, but an improvement in the stability, we are still happy. In fact, this is the case when we detect a 2D or low-dimensional perovskite. Basically, we have a higher stability in the publication we look at. And meanwhile, for molecular and cation passivation, still the stability is not so outstanding. Obviously, it's difficult to compare these values, since also the reference cells that are the lighter color in these columns are different, so the comparison can be pretty challenging. And in fact, this is a review I made with the group of Ted Sargent, and I would like to highlight the importance of these precursors. And looks like that cation passivation can be applied in both architecture. Meanwhile, the formation of a low-dimensional perovskite give us the highest stability. But the take-home message of this talk, or this part of the talk, is about the importance of a full characterization, since if we would like to be able to reproduce the results between one lab or the other, what we need is to identify the type of passivation, and this is going to be fundamental. And in the second part, I would like to start of my talk. I will present the result I achieve in my lab. I would like to start with the inverted structure. And basically, this is the type of perovskite I made. So basically, all the layers are deposited by solution process, and except the metal contact that obviously is evaporated. I need to mention two additional steps for this kind of structure, the so-called DMF wash that consists in the dynamic drop of DMF on top of the surface of PTAA. And this is needed, this additional step is needed because PTAA has an hydrophobic nature. So if you deposit just the perovskite with without this additional step, basically the perovskite solution do not stick. Meanwhile, performing this DMF wash, the perovskite solution sticks nice and well. And the second step is well known, is the so-called anti-solvent that consists in the dynamic drop of an orthogonal solvent on the top of the surface of perovskite or 3D perovskite during the spinning, since and this additional step helps the formation of the formation and crystallization of the perovskite. So basically, I made this kind of device, and after some trials in Technical University of Dresden, I managed to achieve an efficiency above 20%. So we were pretty happy. But of course, now we are talking about passivation. So what I have done is use the additional steps, the two steps I presented before, so the DMF wash and the anti-solvent, to deposit these kind of organic salts. Phenylethyl ammonium iodide, that is one of the pioneers of this kind of organic salts, and also chlorophenylethyl ammonium iodide and fluorophenylethyl ammonium iodide that were pretty new at that time, back in 2021. And keeping in mind what I mentioned before about the 6 factors, using these parameters, so using this molecule with this concentration in this solvent, basically what I find is that the dominating parameter is the concentration. So I'm using such a tiny and dilute solution that basically I'm most likely not gonna form a low-dimensional perovskite. Also, obviously, the other parameters play a role in the formation or not of this low-dimensional perovskite, but this one, since I'm using such a tiny amount, basically is dominating all the others. But looking at what happens, basically, performing the bottom treatment, we started with XPS, and to detect actually the presence of this molecule in the surface of PTAA. And actually, as it possible observed, there is the chlorine peak in the first case and the fluorine peak in the second case that are most likely the identifiers of the presence of these organic salts on top of the surface of PTAA. And looking at during the deposition, what I observe is that basically using the same amount of perovskite solution, in the case we perform just a DMF wash, basically you have to help with the tip of the pipette to spread the solution along all the surface. Meanwhile, if there is some amount of phenylethyl ammonium based molecules, basically the solution spreads really nice and well along all the surface. And looking at from the nanoscale point of view, what we observe is that in the reference cell are present these nanovoids along the interface between the PTAA and the perovskite. And meanwhile, these cations help to stick really nice and well along the PTAA surface. And looking at the PV parameters, what we can observe is that basically there is no change in the VOC, a slight improvement in the current, but a nice improvement in the fill factor, and this can be ascribed to the since the perovskite sticks really well on PTAA surface. Looking at the top treatment, we perform also in this case XPS, and as it's possible to observe, also in this case we find the chlorine peak and the fluorine peak. And also what we have done is to perform an etching step with argon ion beam. And as it's possible to observe, after 20 seconds and 30 seconds in the second case, the peak just disappear. This means that basically we are depositing less than 1 nanometer of this organic sol on top of the surface of the 3D perovskite. And looking at the XY axis, we perform photoluminescence mapping, and we observe an enhancement in the emission along all the surface, especially for fluorophenylethylammonium iodide and chlorophenylethylammonium iodide. And looking at the PV parameters, what we observe is a nice enhancement in the VOC. The current stayed more or less the same, and an enhancement in the fill factor. This enhancement in the VOC can be ascribed to the fact that we are passivating the defects present in the surface of the perovskite solar cell, and also we can observe that also there was an enhancement in the in the efficiency of this device. And performing a double passivation, so bottom and top treatment, what we can observe is that basically we have a stronger emission, even stronger than before, performing both passivation, especially for fluorophenylethylammonium iodide. And this is also, we can say also that basically the deposition happens along all the surface in an homogeneous way. And looking at the PV parameters, we can observe that there is an enhancement in all the PV parameters, since the VOC increase as well as the current and the fill factor. And these can be related to the both effects. So the perovskite solution sticks nice and well, and also we are passivating the defects with the top treatment. And with these, we achieve a nice efficiency that was 23.7, that back in 2021 was the world record for the inverted structure. And we perform a short stability actually, but we were in a hurry for the publication. But as it's possible to observe, basically with continuous illumination taking multiple JVs, we can, in inert atmosphere, we can observe that almost after 2000 minutes, we have no losses in the passivated devices. Meanwhile, the reference cell start to show a slight decrease in efficiency related to the drop in the current. So with this, I conclude the first part of the experimental part. Then I'm gonna move to the second one that is about NIP structure. So the regular structure in which we use the tin oxide, FAPI-based perovskite and spiro. Also in this case, we deposit all these layers by solution process, and we use it as a metal contact gold. We perform the passivation with this molecule, so 4-methylphenylethylammonium bromide, and taking account the concentration and the factors I mentioned at the beginning of this talk, we can say that probably, since we are using 10 millimolar in IPA, we are using a higher concentration, 20 times the passivation I performed in the previous report. And also, since we are using IPA, this one is a mixed cation formula, since contains also methyl ammonium, and we are using bromide, most likely we're gonna form a 2D perovskite. And as before, we started with XPS to detect the presence of this molecule for the passivation. And actually, it was possible to detect the bromide peak and also CnH3 plus peak related of this molecule. So basically, we are pretty sure this organic salt is there. And also in this case, we started with an analysis in the XY axis, so to observe where this organic salt is located. And what we observe first is an enhancement in the emission at 810 nanometers. So basically, the passivation helps and passivates the defects along all the surface of the 3D perovskite. And looking at, and also these can be observed from a PLQI measurement, where we can see that is more than 3 times higher the passivated device respect the control. Looking at the short wavelength, what we observe is that basically there are only some random spots located along all the surface, and from the spectra and performing a magnification, we can observe that basically this is an emission of and can be ascribed to 2 Gaussian peaks. And these can be ascribed to the bromide rich phase and iodide rich phase, since I think we are forming a 2D, pure 2D perovskite mixed halide. So basically we are forming one 2D perovskite bromide rich and another one iodide rich. And from the we would like to observe also from the z-axis where this 2D perovskite is located. And to do this, we perform GWAX measurement with different incident angles. And as it possible to observe, the reference do not have this peak at Q0.37, but is present in the passivated sample. Performing a magnification, we can observe that basically there is a shift of the peak, increasing the incident angle, and this can be ascribed to the different phases that are present in depth along the 3D perovskite. So basically we are passing from the bromide rich phase to the iodide rich phase. And looking at the PV parameters, what we can observe is basically there is an enhancement in the VOC, but also in the current and in the fill factor. And we managed to achieve an efficiency above 24%. So we were pretty happy. And in collaboration with the University of Barcelona, we perform also a stability test, an outdoor stability test. And it was summer back then in 2022, and was pretty high the temperature and also the humidity. But nevertheless, the stability performed really nice and well, since we have almost no drop in the power of the device. So in conclusion, I hope I convince you about the agreement that there is between the experimental result I presented and also the review I presented at the beginning of this talk. And both passivation achieve a high efficiency respect the reference sample, and also an enhancement in stability. But the most important part of this experimental result is that basically we managed to the 3D map of the passivation. And so I hope everyone can reproduce our result, and this can help to better understand the passivation and the results of the passivation. And with this, I conclude my talk. I would like just to mention some other studies we perform. So basically, most of the passivation are studied by trial and error method, but now we started also to use machine learning to screen and predict the best surface modifiers. We studied also other molecules, for example, multiple thiophene-based cations in the inverted structure, basically to avoid the formation of a low-dimensional perovskite. We also observe the passivation in the different perovskite, also in the wide bandgap, for example. And finally, we studied the crystallization of FAPI-based and MAPI-based perovskite to get a better reference and so enhance our result. And with this, I would like to thank my group, especially Professor Giulia Grancini, that support me in all this investigation. And now I hope there is time for some tricky questions.